like to welcome everybody to tonight's Bethe lecture. My name is Ira Wasserman. I'm an astrophysicist here at Cornell. It's a double privilege for me to introduce the Bethe lecture tonight. I'm privileged to talk about Hans Bethe, a giant in 20th century physics. Hans had several careers. Every one was outstanding. It is safe to say that nobody will ever match the excellence he sustained over almost 80 years as an active scientist. Time does not permit a full accounting of the breadth of Hans's accomplishments, but a short summary will give you an idea. Hans began his career in the 1920s when he was among the first young physicists to explore applications of quantum theory. Upon leaving Germany in 1934 to escape persecution for his Jewish heritage, Hans first moved to Great Britain, where he began his lifelong work in nuclear physics. Almost immediately, he became the world expert in the field. Hans came to Cornell in 1935. About 4 years later, he explained how stars burned hydrogen to helium. He received the Nobel Prize in Physics in 1967 for this work. At the core of Hans's career was a fundamental question: how does matter behave at extremely high density? He was a theoretical physicist first and foremost, but fascination with this question brought him repeatedly to astrophysics. Hans retired from Cornell in the mid-1970s after 40 years on the faculty. He helped build the physics department to the world-class status it continues to enjoy today. But even more, he fostered an informal collegial environment that remains one of the characteristics of Cornell physics. After retirement, Hans continued to do research almost right up to his death in 2005. He didn't merely putter around. He led the worldwide effort of astrophysicists to understand supernova explosions. Almost as a lark, in 1986, he solved the solar neutrino problem that had bedeviled stellar astronomers for 20 years. At that time, Hans was 80 years old. How did he sustain such a high level of achievement for so long? He loved solving problems. He was brilliant, of course, but physics was fun for him. For his entire life, he was as enthusiastic and forward-looking as a beginning graduate student. Throughout his career, Hans exemplified personal integrity and courage. During the anti-communist hysteria of the McCarthy era, he was an early opponent of development of the hydrogen bomb. He helped protect his Cornell physics colleague, Philip Morrison, from being dismissed as a result of his vocal opposition to the Korean War and his purported communist sympathies. And he defended J. Robert Oppenheimer, former head of Los Alamos, in his notorious security clearance hearing. He was a forceful and effective advocate for the Limited Test Ban Treaty, which forbade testing nuclear weapons underwater, in the atmosphere, and in space. He was a formidable opponent of the Star Wars anti-ballistic missile program. He was a relentless proponent of peaceful applications of nuclear energy. Hans may yet become the prophet of energy, as Jeremy Bernstein dubbed him. Hans Bethe was a great man. We are lucky that he gave so much to Cornell and left us with such a wonderful legacy. I am also privileged to have the opportunity to introduce this year's Bethe lecturer, John Carlstrom, who is the Chandrasekhar Professor in Astronomy and Astrophysics and Physics at the University of Chicago. John does really cool stuff. In fact, his work is cool in at least 4 ways. First, his research concentrates on observations of the cosmic microwave background radiation, the afterglow of the Big Bang, that is presently at a temperature of 2.73 degrees above absolute zero. But even that is not cold enough for John. He is interested in tiny fluctuations in the microwave background, amounting to 100 microdegrees or less. Second, to do this research, John works in one of the most extreme environments on Earth, Antarctica. On a balmy day, the temperature might reach minus 40 degrees. I don't have to tell you if that's Celsius or Fahrenheit, because the two scales coincide at minus 40 degrees. Now you might think, at such low temperature, one would be able to run one's instruments at room temperature. Not so. For the incredible precision John must achieve, his detectors must be cooled to less than microdegrees above absolute zero. Finally, what is really cool about John's work is that with these incredibly precise observations, he can learn all sorts of fascinating things about the universe. He will share some of these with you in this lecture, Exploring the Universe from the South Pole. John Carlstrom.
Thanks, Sarah. Well, thank you. I guess I'm on. So this is well, first off, Hans Bethe was truly amazing. And one of the, stuff we study is, where did the hydrogen come from? But everything else after that he discovered. And all the stuff in your body was made in stars. That's what we learned from Hans Bethe. This is a picture of this telescope, which I'll talk quite a bit about eventually in this talk. It's at the South Pole. Actually, it's 1 kilometer maybe from the South Pole. As Ira said, we studied the cosmic microwave background with that. But before we just dig into that, I want to give you some background and some cosmology background, what we know a little bit about the universe and how we came about knowing that. So this is a picture, especially you guys. In Chicago, people might not know what this is, but here in Ithaca, on a nice clear night, you can look up and you can see the Milky Way. So this is looking at a big swath of the sky. Actually, not from Ithaca, because this is looking pretty far south. But at the Milky Way, it's all starlight. These little black and dark patches, probably a lot of you know, is not the lack of stars, but in fact gas and dust where stars are forming, and it's absorbing, hiding the starlight, absorbing it and looking black for that way. Right in the middle of the galaxy, there's a lot of exciting stuff there. The light, even in this picture that comes from the center of the galaxy to you, has taken about 25,000 years to do that. So you're looking back 25,000 years. And 100 years ago, this was the universe. That was the universe. We lived in the universe, and there it was. You could look at it. We were part of it. And it's very rich. I'm going to show you in the next picture just to kind of a zoom in, looking down a little bit, which I just think these stellar fields. Maybe we could dim the lights even a little. I think these stellar fields are just beautiful. So there's all these stars. There's bright ones and yellowish and red. Very, very rich. A big branch of astronomy studies stars and how they're formed. But I don't. In fact, I try to look away from the stars. And we know we're in a galaxy. We also know, and I'm sure all of you guys know, that there are other galaxies. But 100 years ago, we didn't know that. We didn't know that. The universe was the Milky Way. And this is, a modern photograph of a galaxy. But that's M31. 100 years ago, there were these smudges on photographic plates, and people didn't know what they were, but they were a real nuisance, so they labeled them and gave them names and warned people not to look at them when they were trying to find comets. So they were cataloged so you would avoid looking at them. But Edwin Hubble, in fact, this is a plate from him in 1923, was studying these and realized that some of what he saw in here were stars. And he knew they were stars. He saw how they varied, and he recognized that they were actually extremely luminous stars. He could identify them, but they appeared very, very dim. They couldn't possibly be in our Milky Way. They were much farther out. And he correctly identified that this smudge was actually another galaxy. So think about it. It's an amazing event that our view of the universe just grew enormously. The Milky Way was one of many galaxies. And so even to this day, most astronomers, or a lot of astronomers, kind of think of the building blocks of the universe as galaxies, just like you would think of the building blocks of the galaxy as stars. And so big surveys have been done about galaxies, trying to see where they are and how they're distributed. And I'm going to show you a video here. I'll just start it. This is done with the data from the Sloan Digital Sky Survey. This is an experiment where they went and they mapped a quarter of the sky, right? You see half the sky around, the horizon. A quarter of the whole sky they mapped. And then they placed images of these galaxies, and they figured out how far away they are. And two guys at Adler Planetarium and Johns Hopkins, Mark Subarow and Miguel Galvo, took that data and made this movie. So you can't really fly through space like this. Each one of these things is many thousands of light years across. But these are all real images that they put together. And so it's kind of neat. It's kind of neat to fly through. It's really cool to see 3D glasses and do this. But I want to point out that it's just not a uniform density. There's kind of some clumps of galaxies. You can see these clumps, and there's kind of some sheets. Sometimes you'll find voids of galaxies. There's structure. It's not just uniform. There's structure there, right? And I don't know how long it runs. I'll speed up. It's really fun to look at this stuff, though. So that if you took their survey and said, here we are in the middle, let's look out in the universe and plot out where all these galaxies are. They looked in two different directions. This is what you get. So again, you can't have this view of looking down like that, but if you could put it on a computer and visualize it, and you can see there's this frothy-like structure, there's kind of this soap suds. It's referred to as the cosmic web, right? So now these are all galaxies. That's how they're distributed. So if we're going to understand, or we think we understand how the universe is formed, we better be able to explain this structure. And it's spectacular. So that's huge, right? We're looking at a huge part of the sky. Let me go again looking at galaxies and show you this picture. How many of you have seen pictures from Hubble like this? Oh, good, great. So it's, actually I think I have my contrast up a little wrong, but it's beautiful. And instead of looking at a quarter of the sky, if you hold your finger out at arm's length, you could fit about 200 of these images on your fingernail. This is looking at a tiny little spot, very, very deep into the universe, right? Very deep, done with the most powerful telescope we have, the Hubble Space Telescope. And of course, every little blip of light in here, it's easy to avoid our galaxy if you're looking at a little spot. We're not seeing stars. Well, we're seeing galaxies, which are conglomerations of stars. But every little blip is a star, all in that little space. Is a galaxy, all in that little space. So that's kind of neat. And I want to give you a number to remember, an astronomical number to remember. And that number is 100 billion. It's the only number I'm going to give you all night to remember, 100 billion. And so what is that? That's the number of stars, roughly, in the Milky Way, in a big galaxy. 100 billion stars. That's a big number. You can take this image, count up all the galaxies, count up how many of your fingernails would cover the whole sky, and multiply those together, and you'll get that in our observable universe, I'm very careful to use this word, observable universe, there are about 100 billion galaxies. Right? That's what we learned from that. So enormous. Also, from work which I haven't showed you yet, but I'll give you the number. It's the age of the universe. It's 100 billion, but that's in dog years, which is, I don't quite know how it works, because I don't think the dog sees the sun going around, the Earth going around the sun faster or whatever, but divide by 7, you get about 14 billion years, age of the universe. And of course, another astronomical number, it's Apple's cash reserve. So it's, we think of astronomical numbers, 100 billion is a good number. But here's what interests me the most about that image. It's mostly black. It's mostly black, right? Your eye isn't drawn to the fact that it's mostly black. You're thinking, my God, that thing is a galaxy, that's amazing. But mainly it's black. The night sky is black, and many of you probably have thought this through. And what does that mean, right? Well, it means we're seeing past the galaxies to a time before galaxies formed. If nothing evolved, you would always eventually see a galaxy, right? But you remember, light, just like when we look toward the middle of our Milky Way, we're seeing it 25,000 years ago. You look to the sun, you're seeing it 8 minutes ago. You're looking in that black. You're seeing these galaxies, which are billions and, several billion years ago, but you see past them. Not past them necessarily that, before, but you're seeing past them to a time before galaxies formed, right? In other words, when we look back 14 billion years ago, there are no galaxies. But it turns out that the sky actually isn't really black if you had, let's say, microwave eyes. It'd be glowing. In fact, it is glowing in the microwave. It's very bright, actually, in the microwave. It's just as bright at night as it is in the day. And that was discovered now nearly 50 years ago by these two guys, Arno Penzias and Bob Wilson. And they were in this crazy-looking telescope. In fact, this is the thing I always like to say, is that this picture, this shows you cosmologist statistics of old, not new. We've gotten better. That all cosmic microwave background telescopes are weird-looking, and half of the cosmologists are bald. But they would ride around in this telescope trying to understand why they were getting all this extra noise. They were at microwave wavelengths, detecting the microwaves, and there was just extra noise. Was it the bird nest that went in there? Was it trees? They were chopping down trees. They did. Anyway, after a couple years, they decided, it's cosmic. And other people, they were not working in the field of cosmology. Other people were immediately recognized that they had discovered this afterglow of the Big Bang. And of course, they got the Nobel Prize for this in 1978. And even though they worked for Bell Labs, I know this is that they don't actually wear suit and ties to the telescope. We don't do that. So that was an amazing discovery. It was really this kind of smoking gun evidence that you had this hot Big Bang, and what you were looking at was the residual light of the Big Bang. And other models, other theories for the universe that it was static, they said no, it was a hot Big Bang. So let me kind of go back to what we mean by that. So this is a plot, Edwin Hubble again, and we're going back in time now, back to 1930. He discovered there were other galaxies. The scale of the universe, he showed us all. It was much, much bigger than anyone thought. And he went a little farther, quite a bit farther, and what he did is he looked at these galaxies. He used a spectrograph so he could measure the emission coming off the atoms, these very characteristic frequencies. And then by using the Doppler shift, if a train's coming at you and there's a big whistle and it's really high-pitched, woo, and it goes by, it goes woo. That's the Doppler shift. You can detect its speed toward or away from you by the pitch. And the same thing with these transitions from that he looked at from atoms. These we call them atomic lines. You can tell that this whole galaxy is moving towards you or away from you. It's easy. Those measurements are easy in astronomy. How far they're moving sideways to, that's really tough. But towards or away from you is easy through the Doppler shift. So he'd plot the velocity he measured versus how far away he estimated. And he was off by, a big factor actually in this. But he got the idea right that the farther away the galaxies were, the faster away from us they were moving. These days, this plot would extend, all the way out here, out to, I don't have my orientation right, but into the next few buildings as a beautiful straight line. It's incredible. But he discovered it. This is the discovery plot. What he discovered, and I'll go through this a little bit more, is that this universe is expanding. It isn't static. So there's another a picture from that period I'd like to show. And you recognize this guy. That's Albert Einstein, a theorist. And theorists generally don't look through telescopes like that. And there's Edwin Hubble. So this picture is poised because deers don't look through telescopes, and Hubble, who is just an extraordinary observer, would never smoke a pipe near all that equipment. But the reason it's here is because Einstein is thinking, oops, because about, I might get the date, I think it's 13 years earlier, he had applied his famous general theory of relativity, his theory of gravity, and those equations to the universe. What would happen? And he applied to the universe, how did it work? And what he found is if there's any mass in the universe, it can't be static. It can't just be there. It's going to evolve. It'll collapse. It has to be expanding. And we knew the universe at that time was the Milky Way. The stars weren't all rushing away from each other. It was, that was the universe. So he added a constant to his equations called the cosmological constant. It's a kind of like, I shouldn't say this, but some students probably do this. They're working a problem, they're stuck. Or they look at the answer in the back of the book. Oh, I got to add a constant. So he added a constant to his equations, which made the universe static. And the oops is because a story has it that he called that adding the cosmological constant his biggest blunder. What it acted like was gravity was trying to pull things in, all the mass, and it acted like a repulsive force to balance that. And actually, there were other good reasons for adding it, but this is, the universe was expanding. Maybe he could have predicted it ahead of time. So let's go through this idea that the universe is expanding, because people get confused on this a little bit. So here's the exercise you can do. Take your computer, a piece of graph paper, whatever you want, draw some galaxies on it, and then don't move them on the paper, just expand the paper. Put it on a Xerox, or if you're on your computer, just expand it. So you do that, 10% bigger. That's the universe a little later. And do it again, right? It's just getting bigger. But we're not moving the galaxies relative to the space. We're just expanding the space. And then you could say, well, we are right here in the middle, of course, right? What does it look like to us for those two time steps through that expansion? And you immediately see the guys next to us, they haven't moved very much. Over those two time steps, they haven't done much, but the ones very far away from us are. And if you were to plot up, the distance from you and their velocity, you'd get a Hubble law, what we now call a Hubble law. You'd see the expanding universe. Meanwhile, let's say you were, somewhere else. What does it look like from their perspective? Right? Well, you just stack it on them, and you get the exact same Hubble law, etc. Right? You can play this game. I won't do it anymore. So the idea is that the space is expanding. When you start asking questions, well, expanding, things are all moving. Where was the middle? Well, any one of those spots is in the middle. In fact, you keep winding it back, they're all in the same spot. Don't ask where did it start, and don't ask what it's expanding into. Well, you can ask it all you want, but you get yourself into a really tizzy and a dead end. Just think that you have a space, and that metric, the space is expanding, not expanding through space. So that's this expanding space. So now we can wind the clock backwards. Just think about all the stuff we see when you look out in the night skies. Think of everything getting denser and denser as it was back in time. And if you go back, so things were about, the scale factor is about 1,000 times smaller. The density would be then 1 billion times denser. That is a time way before galaxies formed. In fact, it's a time before stars formed. It's a time before the first atoms formed. Or if they formed, they were immediately broken up. And so here is a very technical drawing of what that looks like. There were particles of light, we call photons, rattling around. There were electrons. They weren't tied to the protons anymore. The neutrinos, but they, by this time, were just zipping through without interacting. And there's dark matter, but you can't see it. There's dark matter in here, but its gravity would be felt. But the key thing I want to point out is that when you have the photons, you have the light, and it's trying to go through essentially what's a plasma, free electrons, it scatters. It jiggles the electrons, and they make the light bounce around. It scatters. And you're all familiar with this phenomena because you get up in the morning and you look in the mirror, and the light that's coming from you, right, it goes, and the light that hits the mirror, those electrons are free to move and rattle, of course, in that plane, and they re-emit the light back. They reflect it. They scatter. The electrons are like little mirrors when they're free to move. You also know in the morning when you look at that mirror that all this incredible amount of electrons, these huge, Avogadros, and this huge number of stuff between you and that mirror doesn't affect the light at all. You see right through it. That's because it's tied up in atoms and molecules. It's not free to move around. So when you have free electrons, like in a plasma, the light is just rattling around. It's just captured. So you can imagine taking this stuff now, trying to squeeze it, which is what the matter's trying to do, is trying to squeeze it together. Well, it squeezes it, it gets even denser, pulls the photons in it. The photons keep pushing everything and balance, so you let go and it bounces back. It oscillates. Well, when you take a gas and it does that, that just means it supports sound waves. So the early universe is filled up with kind of sound waves, and it's just this plasma. So if we wind the clock forward a little bit from that, let the universe start to expand, the wavelength of light stretches out, it's cooling. You'll get to this time. So here we are, we're looking back. You get to this time, right? So, it's funny, I'm talking about a place, but I keep using the word time. And I mean that, we're looking back in time. You get to a time where the photons, the light that is, can't break up the atoms when they form. They don't have enough energy, right? The electrons then stick to the protons, they stay put, they form hydrogen, and then the photons, just like in this room, they just go right through. They don't interact anymore. And that light just traveling through the universe then. Well, the light, when we look back to that time, the light that happened to be coming towards us, we can see it. That's the cosmic microwave background. And it's no longer a short wavelength that we would see with our eyes, because the universe, remember, space has all been stretched out, the wavelength of the light's been stretched out, and it's now microwaves. But it's there, and you can see it, and that's what they discovered. So actually, when I say this, we look back and there's this surface. It's like thinking of looking at the sun. A photon that's in the middle of the sun and emitted may take 1 million years to get to the surface of the sun, because the sun's all ionized. It's rattling around and bouncing around. But when it gets to the surface, and at last scatters and comes to us, it takes 8 minutes. It just zoom, right? Because it's no longer interacting. So it's the same thing here. All this is rattling around, but when it cools off and the material around it becomes neutral, it just goes. And so this surface is like the surface of the sun, in the sense that it's where we see the light, and it completely surrounds us. It's like an inside-out sun, and it's completely surrounding us in every direction. That's what they discovered. That's the cosmic microwave background. And its light has taken almost 14 billion years to reach us. And if you really get the picture, then I have 2 questions for you. The surface actually is moving away from us. Every day, it's a light day farther away. A light day compared to this diameter is pretty tiny. But it is. If you're seeing what I mean, if you're looking back to a time, the universe is getting a day older every day. And so in fact, you're looking back. And so you can ask the question, if right now someone is on a galaxy right here, what do they see? What do they see when they look at us? Well, they see us not as we are now. They see as we were 14 billion years ago. They would see their inside-out sun surrounding them there, right? So it's not like you're in a special spot. Okay, so that's what they discovered, Arnold Penzias and Bob Wilson. So, and it was fantastic, as I said. It was this hot Big Bang. It led to all sorts of ideas where the elements came from. And it led to this really, really perplexing problem. So this is, trying to write this sphere on a surface. So when I have lots of these pictures of ovals. That's trying to stretch what's surrounding us onto a piece of paper. What they saw, they measured it was 3 degrees or 3.5 degrees plus or minus about a degree. That was what they decided. Of course, the idea then was, well, we should really get detailed pictures of this. That'll be fantastic. We'll be looking at the baby picture of the universe. We'll take a snapshot of what the universe looked like early on. The trick was, or what people didn't notice was happening, is that it was incredibly smooth. That is, the intensity and the spectrum of the light, no matter what direction you looked, was the same. People would build these telescopes and special stuff. They'd look here, compare it to that. They get the same. They couldn't detect any change. And in fact, it took 30 years, almost 30 years, until this satellite by NASA, COBE satellite, I'm not going to remember the name, Cosmic Background Explorer satellite, found that it had about 7-degree resolution, showed that actually there are these slight variations. It's a little hotter here, it's a little colder there, but to a part in 100,000, it was in fact uniform. So you might say, well, so? Think about it. You go out here in the winter, and you pick up a snowball, right? And let's say that snowball is perfectly smooth, like a polished ball bearing. It's accurately smooth to a part in 100,000. You wouldn't think it was an accident. You would think there's some causal reason. Something polishes, there's some causal reason. So when you see the universe being so smooth, you say, well, there must be some causal reason. Something synchronized it. And there's the problem. How is it that if you look that direction, and the light is reaching you from that surface, that inside sphere is reaching you today, and you're measuring its spectrum, and you look that way, and it's reaching you today, and you measure them, they're exactly the same. Those two spots of the universe, for the age of the universe, are just about, light traveling at the speed of light has only gotten halfway to each other. So how could they possibly synced up? You guys all came in and you all had on, bright pink shirts. I think you talked to each other. Right? I would surmise that. What did that to the universe? How did it get synced up? So there's this theory, and it was developed halfway through this race or this in the 80s that was developed actually for another reason, but became explained this, and it was called inflation. And so let's see. First of all, let me get to that. I'll get to that in a second. But you can think, how could it possibly be synced up? So these guys also got the Nobel Prize for this work in 2006, the team leaders. So let me kind of go through it. So this I'm going to show you just a real quick evolution of the universe idea. So we have the cosmic microwave background. We can look at that. We can, and after 30 years, people were able, and I'll show you a lot of advancement in that, able to measure and develop these baby pictures. So if you remove the uniform part and look at the differences, there's kind of this structure, right? And then from that, and this is basically also the bumps and wiggles, this kind of structure you should see in the matter. So the matter starts out smooth, but then you let gravity work, right? And so, is it moving? Oh, it is moving, okay. So gravity, on these conditions, which we can see and measure, and you put gravity and you run your simulation computers, naturally leads to this kind of cosmic web. Gravity working on these initial conditions. So that part of the picture holds together. In these kind of voids, there's voids, there's kind of filaments, there's cosmic web, and at the intersections and stuff, you form big groups of galaxies, and you can get our recent universe. And if you think of this in terms of people ages, let's just call this just retired. Then this would be the first few years. And when we look at the cosmic microwave background, we're really developing from the day of birth. That's the picture we're developing. So let me go back to this inflation thing, because I haven't even called it inflation, but this is the early universe now. Remember, this is the whole thing surrounding us. We've removed, it's really just a glow. We're just looking at the differences now, right? So how do we solve this smoothness problem? And it turns out, well, it's very easy to say. It's easy. In the first 10 to the minus 35 seconds or so of the universe, in some pre-existing piece of space-time, you just expand space a huge amount. It's that easy. You just expand it, and not a little, a huge amount, at least like 10 to the 30 times or so. If you do that, then you say, okay, well, things were in causal contact. They were all in equilibrium, same temperature, and you've stretched it all out, and that's why we see it that way, right? So you say, well, that's I shouldn't have come to this lecture. That's what you say. But that is the theory. And what's more amazing is that this theory is supported by Einstein's equations of relativity. Now, in order for this to be true, that expansion of the space, for this to even work, has to go much, much faster than the speed of light, right? Because otherwise, things would always be, you'd always be in contact. You wouldn't have this problem with light from here and here, only getting halfway at the age of the universe. So things that were in contact, being able to, get in equilibrium, get pulled apart so far that when they send light to each other, it takes longer than the age of the universe for that light to reach them again. So space expanding faster than the speed of light. How many people think that's against the law? Oh, yeah, a few people brave enough to put up their hands. Well, that's what I thought at first too. But it turns out Einstein's equations don't tell you anything about how fast space can expand. They tell you and that you can't propagate through space faster than the speed of light. But in fact, his equations, space can exponentially expand and accelerate forever. I mean, it could really, really get going. There's nothing against that. So that is called this theory of inflation, right? And it's a good name for it. And a little inflation now and then is probably not a bad thing. Inflation leads to this idea that space-time is not curved. And so the way to think about that is imagine you took a crumpled up piece of paper, crumple as much as you want, right? But then expand it, this huge factor. Anywhere you look on that paper, and any place you could see, for as far out as you can see, it would be perfectly flat looking, right? It's because the expansion is just so enormous. So one idea is to try to check that, and I'll show you that briefly. So when you see this picture, you guys at this point you think it's a little crazy looking at this noise all night long. But what you're looking at, especially if this theory is right, is you're looking at quantum mechanical fuzz on the smallest scales having been stretched out to be the largest stuff in the observable universe. And on all scales lead to all the structure and all the seeds of all the matter perturbations, things that lead to all the structure around us today. Quantum mechanics. So we've connected quantum mechanics on the smallest scale, on scales we have yet to even measure physics, to the size of the universe. So one experiment, this is the first experiment I did at the South Pole, was to try to do a first check of this theory. So here's the idea, that we can, these are just sample maps. I like to show this because it's from a freshman textbook. In fact, I think it's even in high school textbooks now. That when you look at the cosmic microwave background, it's the farthest thing we can see. And when you look at it, if the universe is curved, you've all heard or even maybe thought, if I kept looking that direction, really concentrate, I see the back of my head. Right? I see a curve around, I see the back of my head. Well, that's curved space, right? If you think inflation is right, no. The answer is no. It should be very flat on any scale you could hope to measure. It won't be curved like that. So the idea is that if it's curved, this thing that you can see here will look bigger. If it's curved this way, which is called closed. If it's curved in the other way, open, it'll look much smaller. And what that thing is that we can calculate how much structure could have formed in the cosmic microwave background. That's something that people like Ira can calculate and tell me, and we can then go measure it. Well, maybe Ira can't. And so we want to just make the maps and see what they look like. The problem is that Kobe, the map I showed you, it had pretty blurry vision, 7 degrees. So the vision it had was about equal to across your fingers on the sky. That's the resolution it had. It couldn't see structure tighter than that. And to do this, we have to look at stuff with an angular resolution about the size of a full moon, or smaller, right? Which is smaller than your finger, right? So we had to build new stuff. And here is the first experiment we did at the South Pole called DAISY, Degree Angular Scale Interferometer. True to what I said earlier, it's weird looking. It was a very fun project. This was a team. It was me and a bunch of graduate students and some postdocs. And we took this down and built it at the South Pole. And I'll just take a brief thing and say, you must all be thinking, why the South Pole? why go there? So I want to go through that because it's really amazing. It turns out that it's extremely dry. It's the driest desert on Earth, and it's very stable atmosphere. But the dryness is key. If in the morning you want to heat up your coffee, it's gotten a little cold, you stick it in a microwave oven. It absorbs microwaves. Well, if it absorbs microwaves, it also emits microwaves. It's not the kind of thing you want to look through water or water vapor to look at the cosmic microwave background, especially look for these tiny little signals, because the water vapor is giving you signals. And the water vapor is not real mixed in the universe, so when you're trying to compare here to there through our atmosphere, you just see the water vapor changing. It's hard. It's a big, big problem. So it's great to go in a satellite, but if you don't have that option, you just want to go to the driest place you can. So the South Pole is extremely dry. Even if the air is saturated, it gets down to minus 100 degrees in the winter. It just doesn't hold much water. It turns out, actually, it's high altitude, too. You are above a lot of the atmosphere. You're sitting and standing when you're down there on 2 miles thick of ice. There's a continent below you, but it's 2 miles down. And then the sun is a big contaminant. The sun actually is a big source of microwaves, and it gets below the horizon for 6 years. And then there's this other kind of cool thing. These integrations that we want to do, and these, as Ira mentioned, the sensitivity takes very long integrations. And yet, if you're at the South Pole, you could stare out of the galaxy, a good view out of the galaxy, through this pristine atmosphere. And all you got to do is stare at that same spot 24 hours a day, 7 days a week. It doesn't move. The Earth rotates underneath you, but it just spins. So all you need is one azimuth bearing, and then you can just keep staring. You go very, very deep. So it's a kind of unique location. And of course, what's absolutely critical, or we wouldn't be able to do anything, is that there's a station there. Right on the South Pole, the National Science Foundation has a research station. And so there's great support. So here's a picture of a sunset, time, just exposure. The sun takes a day or so to set, but it takes 6 months to come back. So they're just opening the shutter, and then it gets very cold, very good conditions. And so here's some images we made with that funny-looking telescope of patches. Now, just tiny little patches. We put them all together, but they're patches spread around on the sky, circular patches. Each one of these patches is 3 degrees across. And remember, the whole map in the resolution of Kobe was 7 degrees. So it's much higher resolution. And I don't know if you see it, but they all look like noise, but they all look kind of similar. Right? They all have kind of same structure, same sizes, kind of blobs, same size blobs. And that is not the resolution of the instrument. The instrument was much higher resolution. That's what the universe was doing. Around the same time, actually a little bit earlier, this balloon went up. And and had a smaller telescope at a higher, shorter wavelength, doing similar work. And these balloons are cool. They go on the coast of Antarctica, and then they get caught in what's called the polar vortex. They rotate around the Earth. It takes about 25 days. They see it coming again, and then they cut it down. And they hope it doesn't land in the ocean. Usually they land somewhere in the snow, and then they get dragged around, but they go out and get their data then. Boomerang was a very famous balloon experiment, too. So you go to this textbook, the very next page, it says, well, which is the right one? Is it curved? Is it flat? Or is it, what would be closed? What's right? And then they show you the data from Boomerang, so I always feel a little burnt by that. But and it's this. It's flat. The universe is flat. Right? Uncurved is maybe a better way to look at it. It's three-dimensional, space, but light rays, if they're parallel, they just stay parallel. They don't curve in, they don't go away. Right? So Einstein taught us, and you've seen this, that matter curves space, and it's the curved space that gives you gravity. Well, if you know the curvature of space, it turns out that you can run this backwards, you can figure out this stuff. And so for flat space, the average density is at what's called the critical density. So you're measuring this curvature, and you're solving, through Einstein's equation, you solve for the density of the universe. What's it made, what's in it. So what we get is the average density of the universe is about equivalent to 3 3 hydrogen atoms in a cubic meter. So I don't know what you guys think about that. We've never, ever produced a vacuum on Earth as good as that. Not even close. That's very, very low density. But that's it. That's the average density of the universe. But of course, for gravity, you get a lot of cubic meters. That starts to add up, and it starts to attract. You can form galaxies, and all that structure comes from this meager little low density. And if you want to know how low that is, here's the density in this room. 10 to the 27 or something, 20, equivalent. It's not all hydrogen, but equivalent in weight and mass, atoms per cubic meter. And thank God, or we'd have a hard time breathing and living. And so we live in a very, very special spot. So I want to be a bit more quantitative. You guys have seen things like this, graphic equalizer, someone's playing the radio, and you see the bass down here, and you see the bass thumping as it goes along this rock. But you can draw a spectrum of music. We think that way. We're brought up to think that way. Even though we're hearing a time variable oscillation in sound, we have no problem thinking, there's this bass, I'm going to turn the bass up, I'll turn the treble down. We can think of it in waves, right? But it's not like these different waves are coming in. It's just this vibration we're analyzing. Well, you can analyze anything that way in terms of waves. And so just like this characterizes the spectrum of sound, we can characterize this, and I didn't want to, we can make a similar spectrum, forget the buzzwords there, to characterize a map of anything, right? You have some form, you can say, well, it's made of these long wavelengths, these short wavelengths, and you can make a spectrum. And that spectrum, when you make a spectrum of a maps of the cosmic microwave background, actually, and it's showing you those sound waves I mentioned earlier. It's revealing the structure of the sound waves in the early universe. And you've seen this, right? So you've gone in, and you can go in your iPod and adjust and shape, more bass and that. You can do this. So this is apparently the New York Times. I got a picture out of date. No, thinks that everyone does this, and this is just common stuff. So our maps were there, and they plotted and made this spectrum. Well, we gave it to them. They didn't actually do the analysis. But this is what we do. We do the analysis, and we think of them, compare them, spectra. And then theorists can say, well, this is what things should look like. And so this is this thing. This feature we are seeing is like a bass note. It is the fundamental tone of the universe, of the early universe. It's ringing like a bell. And then it has a harmonic and another harmonic. And you'll see even more in a little bit. And so this in the New York Times is what they call it, listening to the origin of the universe. Right? Now we don't take, our telescope is not a microphone. We're measuring the map. But what we're actually measuring, what's causing those ripples on the sky, is sound waves in the early universe. So since then, Dave Wilkinson designed, and his team built the microwave anisotropy probe, WMAP. This is an image from COBE. They matched essentially the same resolution we did with DAISY and did the whole sky again. So now we can take this whole sky and do that analysis. How much are in long wavelengths, how much in short? Do that same analysis and make a spectrum. And a lot more data, and it's really clean. There's this note. There's that pitch. There's a harmonic, another one, and then it's getting noisy. Right? And so if you think about it, what makes one instrument sound different than another? Right? And it's these overtones. A violin has, incredible amount of overtones. That's why it has that very rich, very interesting sound. If you had your computer do a beep, it has, just that one tone. It sounds horrible, right? Drives you crazy. You can't stand it. But as you add these, you get a richer and richer sound. And just by looking at, well, I can't do it just by looking, but you could, just by looking at this, figure out what is the instrument. What's making that sound? What's causing that? And the same is true for the cosmic microwave background. We can analyze those waves and essentially tell what the universe is made out of. And here's what you get. Ordinary matter. This is the pie chart. What makes up the universe? What stuff makes up the universe? So this blue thing, right? You could say, well, that's not important. That's not important. We don't have to talk about that. But that's everything we know. That's all of the stuff that's in textbooks. That's all this. You name anything. You know, you're everything. That's it. 4%. 4.4%. We're getting it down much sharper precision. That's it. Dark matter. Okay, dark matter. How many have heard of dark matter? Okay, good, because I'm not going to say too much about it. Dark matter is what, astronomers, since starting with Zwicky in the 30s, have been telling us there's got to be this extra mass out there to hold galaxies together, to hold clusters of galaxies together. We need this mass, and we can't see it. It's invisible. It doesn't interact with light. What these measurements tell us is that, yeah, there is a lot more dark matter than ordinary matter, but it doesn't fill the whole thing. And furthermore, what these measurements tell us, because we're looking back, certainly, the dark matter, you might say, well, it's a bunch of failed stars, a bunch of planets. No, those didn't exist in the early universe, and we're measuring these sound waves in the early universe. What we can show, what these data show, is that dark matter is some new form of matter, not some just rocks or clumps or things that just happens not to be glowing. And of course, that gets physicists very excited because they want to discover new physics. There it is. What is it? We don't know exactly, but maybe we'll find out this decade. So dark matter dominates ordinary matter just like it does in galaxies with about the same ratio, even though we're looking way back before galaxies formed. So galaxies are made out of this stuff. But there's this missing part, right? And that we call dark energy. And I think they call it dark energy because they wanted the Department of Energy to fund research on it. Dark energy really, it's energy because in Einstein's equation it acts like a source of energy in space. Dark in that we don't see it. And that pretty much sums up what we know about it. The amazing thing is that, and you could say, well, how do we figure that out? We can see how these are working in sound waves, but how do we figure that out? Well, we use this technique which you've been hearing a lot about in the conventions and the election. Very sophisticated technique. It's called arithmetic. Remember, I already told you we know what the whole density is, right? We get that just from measuring this curvature, just by measuring the size scales, this stuff. The harmonics in that tell us what it's made out of, and they don't add up. I've heard it's applied to tax plans. Here it's the universe. 3/4, roughly, and we know these numbers much more precise now. 3/4 of the stuff that makes up the universe today, we really don't know. We don't know. We're knowing more about it, but we don't know much about it. We think it's very uniform. I think it's everywhere. So that's equivalent of about 2 atoms per cubic meter in mass energy everywhere. It doesn't seem to clump up. And the explanation, which fits it so far, is that it is Einstein's cosmological constant. And in today's kind of physics, you would identify, if you wanted to put some physics to that constant, it would be the energy of empty space, the energy of the vacuum, right? It's not zero if this is right. It's about the equivalent mass energy density, about 2 protons per cubic meter. Very tiny, but not zero. That's one explanation. Along this same time, in fact, a little earlier than that, this group of people, 2 big teams and others as well, were looking at distant supernova. And what they were trying to do is they figured out a way to characterize how bright the supernova really was, like a standard candle is the jargon. And they were looking for what they called, what was called in literature at the time, the deceleration parameter. There's all this matter in the universe. We know Einstein's equation. We can, get rid of the cosmological constant. We can apply those equations. The expansion of the universe should be slowing down. And now that we can go and look very far out, we can measure the rate of expansion, and we'll see how it's slowing down. And then we can go back through Einstein's equations and get the total density of the universe. That was the idea. They found out that the universe wasn't slowing down, that it was speeding up. It was accelerating. Right? And they got the Nobel Prize for that just last year. So, that's great. We have dark energy. It all fits together. What is it? And that's where I'm getting to our experiment, finally. So the idea is that you can go and measure, at the rate of slowing down or speeding up. You can do geometrical tests. That's what the supernova people are doing, and others. Or you can try to measure, is general relativity really right? If the space is accelerating, that's really happening. It'll really affect how you form objects. You can imagine two things are trying to, through gravity, they're pulling together, but the space between them is not just expanding, but accelerating. Well, they may never win. They'll lose that battle. If they're far enough away, they'll lose that battle. And you won't form big objects. Meanwhile, if this is wrong and it's just gravity, there's nothing like dark energy, eventually they'll win, and gravity keeps winning. It keeps accreting. You keep forming bigger and bigger objects. So here is the cartoon. Imagine you have all this dark matter in the early universe. And remember, the density, in the early universe, the density is much, much higher, right? It's getting diluted as it expands. And then you've got this dark energy, Einstein's cosmological constant in this model, trying to be like negative gravity, right? It's trying to push things away. But it's not that important. It's only this very low density of the vacuum. But as time goes on, the universe is expanding. The matter, it's just getting diluted. But if this is a property of the vacuum, it's not changing. It doesn't change at all. So he knows, this guy knows, he's smiling. He knows, I just wait. And today, he's winning by, 2 to 3 to 1. He hasn't done a thing. He's just waiting out. This guy's looking desperate. And the dark energy is winning. The universe is accelerating. He's won the battle. And he's like dreaming of the future, when it's all just me. The universe is going to accelerate, exponentially expand, and in the distant future, cosmologists won't have any work to do, because when they go to look out in the heavens, things have been pushed out of the horizon again, and they only see the Milky Way and say, that's our universe. And Hubble wouldn't have found, actually, wait about 5 billion years, we'll collide with M31 and build one big, massive galaxy, and Hubble won't have any other galaxies to find. All right, so we were born in a good time for cosmology. I agree. It seems kind of crazy. And this is what our newest project, that great big telescope, was to try to learn a bunch of things, but one of them in particular was to try to learn more about this. So what we're going to do is we want to look at the biggest objects that the universe has ever formed. And those turn out to be clusters of galaxies. They're beautiful objects. Here's a picture of one. It has these galaxies in the middle. Really dense. This thing that looks like a ring. This is actually the same galaxy. It's not part of the object. It's way in the back. But there's so much mass here that the space the mass is curving the space, and so you can see that same galaxy in many different lines of sight. It's called gravitational lensing. It's an amazing thing. It allows you to actually calculate the mass enclosed. And these are huge, 100,000 times the mass of our galaxy. Biggest things the universe has produced. Nothing bigger. There hasn't been enough time to produce anything bigger. It turns out these things are rare. They're pretty rare, these massive ones. And they take billions of years. They essentially take the age of the universe to form. So when they formed in time, cosmological time, how big they get and how they grow really depends on how gravity works on large scales and how this tug-of-war that I showed you between dark energy and dark matter, who wins that tug-of-war when. And we know, thank God, dark matter won at some point because we're here. But when? When did it start losing? Is it losing? So these are rare and hard to find, but if we could find them all, we could put together this tug-of-war through cosmic time and test that against models of dark energy, especially in particular test to see if Einstein was right. So that's what we want to do. Here's a fun simulation by Risa Wechsler and her collaborators of showing, similar to before, but showing how a galaxy cluster will form from those very, very small perturbations in the early universe. You can see it's just gravity coming together. This space, although you don't see it, the space itself is expanding, so it's slowing down the way things are falling because this co-moving space is evolving. But you can see it just keeps accreting matter and pulling stuff in. And you can also see how if you have something accelerating the space, moving it apart, it's going to retard this. Right? And then we have this incredible object, galaxy cluster forming. So here's another this time from the Hubble Space Telescope. You can see all these arcs from background galaxies and very, very rich things. Well, it turns out that, in fact, the galaxy clusters, it's kind of a funny name for them. There are a lot of galaxies in them, but they're mainly dark matter. Most of the mass is dark matter, not associated with individual galaxies. Most of the ordinary matter in these things, though, is not in the galaxies. It's in this gas. And so this purple, right, I changed the color. I didn't change the color, really. I added the gas that's emitting X-rays. The purple is data from the Chandra X-ray Observatory, Space Observatory. And it's very, very diffuse. It's just sitting there. I turned off the optical light. That's what the X-ray emission looks like. That's not a model. That's the X-ray emission measured with the Chandra, NASA Chandra satellite. It's very uniform. It's filling this deep potential well, and it has about 10 times more mass than all the galaxies combined. So the galaxies are little test particles. It's mainly this hot gas, and very hot, right? It's such a deep potential well to fall into. That's like 100 million degrees. So 100 million degrees, even iron gets ionized. Hydrogen is completely ionized. Helium, everything's ionized. So we have this ball of really hot, massive gas between us and the observable, the cosmic microwave background. So it's like having a bunch of little mirrors again. You have all those free electrons. So what happens is if you were to look at the cosmic microwave background, the cosmic microwave background photon, it's trying to go through, it sees all this hot gas. Well, it usually goes right through. But about 1% doesn't. And of that 1%, it tends to get bumped to very high energy because this gas is really moving. It's really hot gas. And so when you're down here and you look with your telescope and you're looking at these long wavelength photons, there's a bunch missing. They're missing. You see a shadow against the cosmic microwave background, right? And what's cool about this is Rashid Sanyaev and Zeldovich came up with this in the 70s, is that if you can detect this effect, and I'll say a little bit more about it, if you can detect it, you can detect it anywhere, even if that galaxy cluster is across the observable universe. It's between you and the cosmic microwave background. You can see it as a shadow against the cosmic microwave background. Not a very deep shadow on small scales, but you can see it. And if you can do that, then you can find all the massive galaxy clusters. And then you can put together this map and trace this tug-of-war between dark energy and dark matter. Maybe learn something. So there's Rashid Sanyaev. I don't know if you've seen him when he was in graduate school with his advisor, Zeldovich. So we built this telescope to do that experiment. And there it is again. 10 meters. It's a 700,000-pound Sanyaev-Zeldovich imaging machine. That's how I think of it. If anyone says, oh, that satellite dish, I'll get insulted, so don't say that. It's a very highly accurate telescope. It's clean, low noise. The rays come in here, and so they don't interfere with anything. It sees a big field of view for these kind of telescopes. It can see a full degree, a square degree at once, like your fingertip. And 10 meters, the part of it, we don't quite use the full 10 meters because it's quieter, it turns out, if you don't use the edges. It gives a resolution for looking at the cosmic microwave background that your eyes have for looking, about an arc-minute resolution. And then we have all these detectors and stuff. I'll talk a little bit about that. So here's the team. Unlike DAISY, where we had, there was, I think, 8 of us, this is more like 90 people at this point, because there's so much science coming out of this. This is Kyle Story, who was an undergraduate here. He's now working with us. And so now I want to take you kind of on a travel log and a tour through the Air Force planes. We get to ride in these really cool planes. They have names like the Globemaster. And the Globemaster, the C-17s are amazing. They can lift, I think, 140,000 pounds of cargo. And here's some of the cargo going in. Inside, they're like a barn. They're really amazing. Every seat is an aisle seat. And there are no window seats. Those little windows, as you can see, in the emergency doors. These are so you can look at the engines to see if they're on fire or not. That's about it. Your cargo. And nevertheless, we're really happy we have those little windows. And we can see here we start in the South Island of New Zealand. This is going down and starting to see the coast towards Antarctica. You land on sea ice, frozen sea ice. In fact, if you go in November, in fact, I go in about 2 weeks. If you come out in January, where your plane landed, where this incredible plane carrying, well over 100,000 pounds landed, is open water. It's kind of neat. They moved the runway to a different ice. And then there's this town. I don't know, town's wrong. I don't know what you want to call this place. McMurdo. These are dorms. It's all just transients. It's, it looks pretty bad. It is. It's not a very nice place, but the view, I should actually show you, the view is spectacular. You just look over ice. You'll see these mountains, and they're beautiful, and everything's bright white, and it looks like you could walk through them. And they're 70 miles away. It's just so crisp and clean. It's amazing. This is a cool thing. This is, does anyone know what that is? It's a Polynesian hut. Do you know how it got there? Scott, who 100 years ago went and did a hike to the pole, didn't make it back. This is the hut, and he picked it up in Polynesia on his way, a prefab hut, and set it up there. And so this is, it was 100 years ago in January that he made it to the pole. And this is where, they stayed the winter before and made their preparations for their trip. And you can see more of McMurdo. This is where the icebreaker comes in and offloads stuff. You can actually go in the hut, and it's pretty much the men just left it. And you can see, as it was, you can see where they were actually ripping parts of it down to burn. I don't remember how many men were in it, but this is about half of it. It's very, very small. And you see things like this. Does anyone have a clue what that is? I'll tell you one thing, it's 100 years old. It's seals. That's what they would eat, and then they would burn the oil, and they just have been there for a long time. But it wasn't penguins. The penguins are very cute. This is when we went down, it's called Hut Point, where we were there, and the icebreaker had just come in, and these are Delhi penguins, all these penguins were coming up. Very cute. And we thought they were just happy to see us. And it turns out they come right up. You're not allowed to walk towards them or do anything. There's all these trees. And they would then walk right past us, and they all went to the icebreaker. And then we got it. The icebreaker is like God to them. It brings the water from many, many kilometers away right to the land, right? And they flocked. Thousands of them came that day. It was amazing. Anyway, our beautiful little vacation in McMurdo Station ends as quick as we can make it end. And then we get on this thing. So now we're on the Hercules, LC-130. And the cool thing about this for you guys is that these are very rare, these ski equipped. You see this big ski, because they needed to land on the snow at the pole. They land on skis. And it says U.S. Air Force. I can't make it out. I don't think this is one. The New York Air Guard runs this service. So it's you guys, and I don't know who pays for the Air Guard, but it's the New York Air Guard. And I remember getting into one, and right up here, that's what I was looking for. It said the Spirit of Syracuse, which was kind of, I'm from New York, so I'd like that. And they'd love it. They go down there. But anyways, the New York Air Guard has this contract to operate these ski-equipped Hercules, which are very, very rare. They're not allowed to sell any to other countries. Apparently, they can surf on the water and sweep for mines, and we don't want other countries to do that, I guess. Anyway, you get on this thing. Again, you're packed in as cargo, and you can look through those little windows. Of course, the windows are looking at engines, so there they are. But you go over, you climb up, you go over the Transarctic mountains, and these incredible glaciers you can see. They're just phenomenal glaciers, and you're getting up to the high. These mountains keep the snow in. That's why it's built up so much into the high Antarctic plateau, and eventually then to the South Pole. So that's it. That's what it looks like. There's nothing for hundreds of miles. and no mountains or anything. It's just flat. It's like being out on the ocean, and for some reason it's frozen solid, and you're just walking on it. There's a station. There's a building. And this is I don't know what you want to call this. It's where they store stuff that they don't want anymore. I think you would call this a dump. But it's very valuable to be able to go find things there. Here's our telescope there, and this is this very long runway for landing. So here we are landing. These LC-130s, every one that arrives or takes off to go there, no matter what's in it, people, 2 people or a bunch of people or all the cargo, they're maximum loaded with fuel. It's at their maximum lift. And then when they get there, they're not fueling the plane, they're taking fuel off. So the whole station runs on jet fuel, JP8, everything. So every plane then is filling up the bladders and the tanks for the winter. It's the equivalent of what they would call 200 tanker flights a year. That is, if they were just fuel, to get the station ready to run through the winter. Right. And the other thing is that everything you see down there, and the telescope I'll show you, came out of the back of one of these, every piece. So we'd like to, especially in a telescope, we'd like to have one big weldment, but you can't. You can't weld down there, it's too cold, it takes too much time. So everything has to be 8 feet by 8 feet and up to maybe 16 feet long, and under 26,000 pounds. So that changes what you do if you're used to building things. So you build, there's the new station. Again, all that came in these planes. And then here we are getting ready to build the telescope. So this looks like ice fishing, but it's not. We dig a big hole, then you compact it with bulldozers, and you level it, let it sit, do another layer, centimeters at a time, so that you can build essentially this compacted snow or ice foundation. Otherwise, your 700,000-pound telescope is going to be slowly sinking. And then you build kind of pontoons on that, and then a steel structure comes up, and then you put everything that you want access to, everything that has to work flawlessly, you make it warm. So the telescope goes up through a building. We heat the building. So while that's going on, I'll come back to it. A bunch of us were then building the most crucial part of the telescope, which was the reflector. So it's this very high-tech stuff. This is carbon fiber reinforced epoxy on an aluminum honeycomb substrate. And the idea is that we're going to 10 meters, but when we tip this thing up and around, we can't let gravity distort it more than about the width of a human hair from a perfect parabola, or the experiment won't work. And steel is not strong enough. Steel will flex too much. So this is to do that. It looks sunny. It looks like, oh, that's nice operating temperature, but in fact, it's not. It's about minus 45, but it's always very, very sunny when you're down there in the summer. Of course, the sun's just going around. And then here is Jeff McMahon, postdoc, and his job was to figure out how to get all the panels. Of course, we did a test build, actually, in Texas, but working in that cold, we had to set what turns out to be almost 1,800 adjusters for all the panels, all within a micron. And then you set it, and you measure it and iterate, and that has to be right. Meanwhile, then the iron crew is building the structure up through the building. So this now has the bearing on top, and then building on the bearing, and the yoke. And then there was this day where all these efforts come together. This is the day where the station in the middle of the summer, middle of the austral summer, this was a little before Christmas, the whole station comes out. You know, it's about 250 people then. They all come out. And you know, I didn't know you were so interested in telescopes. And they're like, oh, I don't care about telescopes, but if they drop that thing, I'm not going to miss that. You know, I got all the way down here and I missed the drop. They didn't drop it. Putting it together. And then finally, the crew is very... Actually, this is from a different year, but to give you a sense of the crew down there working on it. So here's the telescope. Here's the other feature, right? So this stuff that looks like it's just styrofoam is just styrofoam. It's keeping this encoders and motors warm. That's making the telescope change in elevation. This whole roof thing moves inside the building. So here's inside the building. You can see that's where all the control is. But there's a door. This is our receiver thing, you know, where our camera is. That comes down and the roof slides out, and then we have a little high bay. So we don't You just have to design things that you always can work on things in the warm, and that things stay warm. So this cabin is kept warm. But the telescope, of course, we're allowed to get cold. So there's our receiver coming down, and here is putting on our little 1,000-pixel camera. We're very proud of this 1,000-pixel camera. It's 10 times bigger than any other camera and pixel count that had been done at microwaves. I know you guys have your 10-megapixel cameras, but you didn't have to build every pixel. And you didn't have to take every detector and cool it to 0.25 Kelvin above absolute zero, or minus 459. So these are our home-built detectors. They're insanely sensitive. And then we got it all going in our first year, and then we leave our winter overs. And so these are our heroes. Our first year with Steve Payton and Zach Stanishevsky were our winter overs. But every year, the crew, we do our upgrades, whatever we're going to do, and then around Valentine's Day we leave, and 2 people stay. And they take the next flight out, which is usually in early November, go through the winter and keep it going. And so if any of you are interested, let me know, especially if you're talented. And the amazing thing is this is Dana Rubius. He did it in 2008. Then he did it in 2010. There he is. Then he did it and convinced his partner to do it again 2 years back to back. And then he took a year off, and he's going again next year. So obviously it's a great thing to do. I mean, they love it. So I encourage you to let me know. Anyway, we make maps with it. So all that was to make these maps. So here is our map. We didn't do the whole sky. We did about a 16th of the sky. And this is the highest resolution, arc minute. We're not talking a degree anymore. We're talking a 60th of a degree. And the highest sensitivity map ever made of this background. Here's WMAP. You can say, well, it looks the same. What's the point? Well, the point is that you can't see it because the detail doesn't show when you're looking at 2,500 square degrees. So let's zoom in on 50 square degrees and filter out some of that pesky large-scale structure, which is that big peak in the base note. Let's get rid of those waves. Let's not have those. And we still see there's this structure. We see this ripples, and that's not noise. That's the sky. And now we can take a power spectrum, the spectrum of that, and it just keeps going on. There's that fundamental peak. That's our universe, ringing like a bell with an overtone, and the overtone, and the overtone, the overtone, the overtone, the overtone, etc. This curve that goes through all these points is a curve that's theoretically derived. It's not drawn to fit through the points. There's some parameters so you can make it fit better or worse. But the fact that it has these peaks and that spacing is not something that you can change around. That's what you get if you have a mechanism like inflation, something that has synced everything up at once. That's the only way I know, anyway, to have generated that spectrum. So this is, you don't like inflation? Well, we who do these, we're getting used to it. It keeps fitting all the data. So I just like to show this because, well, actually we haven't quite got this published yet. So it's a sneak preview soon. But it's just spectacular. Now here we are looking at the largest scales of the universe. The universe kind of as a whole, and it's ringing like a bell. And not only that, that's what inflation tells you it should be doing. It's in agreement. Here is just the other thing we see, at this very high resolution, we see these little bright spots. And those tend to be, those are galaxies. Most of them are black holes, which are exciting things. But even more exciting to us is that some of them turned out to be these lensed, again, gravitational lenses. This blue is the Hubble Space Telescope image, and the red is using this beautiful new telescope called ALMA down in Chile to image at high resolution what we see. And so we found these very, very rare early galaxies that actually become the precursors for the big galaxies around us today. So that was kind of fun. But we weren't looking for that. We were looking for galaxy clusters. Remember, we're going to do this dark energy experiment. So we're looking for what? We're looking at the cosmic microwave background, and we want to see holes. Really, we want to see where's it missing. And so that would be like black spots. And of course, there they are. So this telescope, and this was the first time these had ever been discovered galaxy clusters, this method. So we really, really took a gamble. The National Science Foundation took a gamble this would work. And it did, right? So that was very, very big news. And there they are. And we don't find just one or two, we find lots of them. Now, remember I told you that's what we want to do, and we can find them wherever they are. They could be across the observable universe. We don't know how big the real universe is, but across the universe we can see in our finite lifetime of the universe, we'll find them. But we don't know where they are. So we have to then take everything at our disposal, and of course people are excited by this, so they give us time on the X-ray telescopes to look. Now we know where to look. They give us time on the Hubble to look, ground-based, big, beautiful telescopes, the Magellan. They have to be in the south, though. And we look, and then we can look at these things, find the galaxy cluster, and then we can look at the Doppler shift, the light, and figure out where it is in this beautiful Hubble flow. You know, what is its redshift? So here's one. It's relatively close by. Oops. And the contours are where we with our 1 arc-minute resolution, can say where it is and show you kind of our signal to noise. And there it is. It's close by. The galaxies look kind of yellowish. Here's one that actually got a lot of press recently. It's farther away, a little more than twice as far away. And you can see all these yellowish galaxies getting a little more yellow. This is an amazing object. We're finding all the most amazing galaxy clusters. In that this thing, when we told people about it, gathered a lot of news. And here it is. It's the cosmic supermom. What it is that we know these galaxy clusters form, and the galaxies right in the middle tend to be huge. And so the thought for years was, well, all that gas and stuff is falling into the center and forming this big galaxy cluster. And they had all this theory, and then they looked for it. They couldn't find any that were doing that. They couldn't find any galaxy cluster that worked. Instead, they found the center galaxy was pushing all the gas away from all this activity. And so this one, we finally, caught one having and forming stars at the rate of about 2 a day. Our Milky Way, 100 billion stars, it produces 1 star a year on average. This is doing 2 a day. So it's a record for that. Here's another one, and you can see, whoops, it's not on your plot, it's on mine. So here's one going farther out again, and now you can see they're getting kind of red, right? Because we're seeing, they're harder to find. And here's one now getting quite far, more than halfway to the edge of the observable universe. And here, actually, this is infrared data. It's red, we looked red. And the optical, you can't see anything. There's nothing there. Right, so we thought, oh, maybe it's wrong. And we look in the infrared, but now it's been shifted and we see it. And we've seen them now even farther. And this one, of course, is got a lot of news too. It's really far away, and yet it's incredibly massive. So it's early in the universe, and yet it had all that mass. So, monster galaxy found, master galaxy cluster. So here's the reaction to this thing. There's a lot of news, science news and Nature. This is you can detect them. It's working. We're going to be able to understand and get this tug of war done. Our reaction was, let's have a party. And that's at the South Pole, and all these people helped us. We had big parties, and this was great. So where are they? And so this is a plot. We're still doing analysis, but this is a plot. Every little black square here represents one of these new discoveries, right? And I put them on this plot. This is look back time in the universe. Remember that we can look back. We see before stars, that was about 14 billion years. That's how old the universe is. And we're getting pretty far back. This fact that there's an edge here, that's because if they don't have enough mass, they don't scatter enough of the cosmic microwave background, we don't see them. Right? We need a certain amount of signal. So we don't have a redshift. We don't have a distance, something that prevents us from seeing things at big distance. But if they're not very big, we don't see them. And so you can see a few things. One is that when we go farther back in time, the universe was denser and hotter, and it turns out the signal gets bigger for a given amount of mass. So it's completely contrary to what most other people think. We go back farther in time, and we're more sensitive. Farther away, we're more sensitive. These are, the red and green is not our data. This is other surveys looking for galaxy clusters. And when they go back, things get dimmer. And so up close they can see really really, not very massive things. But then when they go farther back, they can't find them. They've lost sensitivity. X-ray, for instance, are very hard to find them in X-ray, unless you know where to look. So here it is, this map. And you can say, well, where are these guys? And the answer is they don't exist. If they were there, we'd see them. Right? So we have now, in front of it, this is about 70% of our data we've gotten the redshift. You are basically seeing the formation. When did they form? Well, they started forming at this mass about here. And then they really formed a lot. And it turns out that after about here, they stop. Actually, more like here. You don't form any more. Something turned it off. Right? Well, that's more or less what's predicted from Einstein's cosmological constant. So this is always fun. This is a press release that our government agency, the people who give us awards, put out. So it's always nice to know they like you. And it's two things, right? So they're talking about dark energy, but it also turns out we're learning about neutrinos, and that's another talk. But what about this dark energy? So far, it's the precision we have so far, and we're working to improve it quite a bit. This independent test, which we're measuring growth, we're measuring general relativity effectively, and gravity, says Einstein looks like he was right. Right? So that's where we are. So it's in our sights. We'll figure this out. And as precision gets higher and higher, we want to look for, is there any subtle variations? Is it really as simple as bizarre as it might sound, but as simple to say there's just an energy of the vacuum. Empty space has energy. That's what it looks like. We're finding hints of lots of other interesting things. We're finding these new galaxies, those dusty ones. We're finding information about neutrinos. We have that wonderful beating of the universe, which allows us to hone in and get much more higher precision on all of what the universe is made out of. And we're already starting our next experiment, which is to really see if we can test inflation in the universe by measuring phenomena at the very early time. So I want to show you, that's the end of the science story. But while you're thinking of really hard questions to ask Ira, I want to show you some parting shots. So when you're going to, if you have a telescope at the South Pole and you're going to have people go down there and spend the winter, give them really good cameras and good video equipment, and then they will send you back great stuff. So there's the aurora. It's not the aurora borealis, it's the aurora australis, southern lights. And just last week, they sent me a video, which is, the video is actually many minutes long. I only have a piece of it here. It's just spectacular. So our little telescope, well, little in this picture, it's a fisheye lens, right? It's just scanning back and forth, and all this is going on above it. This is about 200 times sped up. Yeah, good question. Anyway, I just think it's spectacular. You can see the Milky Way coming in. These things that go across, those are satellites. They just go on and on. And that's particles coming from the sun, being captured in our magnetic field, and then highlighting, glowing and highlighting the magnetic field structure of our Earth. And when we get these pulses here in the south, similar ones at the same time are happening in the north. It's just spectacular. Anyway, thanks for listening, and you can come up with your hard questions. Okay. I see it's late.
I know it's a little late. We'll take a few questions, but before we take questions, I have an extremely important announcement to make that all of you will be happy to hear. Namely, there's a reception for our Bethe lecture in 401 Physical Sciences building. Everybody's invited. So let's take a few questions for a few minutes.
Yeah? That's a pretty technical question, but I'll repeat it. How do you calibrate your data? And so there's a number of ways. One is, of course, it's the same detectors doing this work even on large and small scales. So we can calibrate those against other measurements, WMAP, for instance. We could do it statistically through the power spectra where they overlap as well. But in addition, we every day map H2 regions, every single day, and monitor that, and we do elevation dips. So calibration is a big, big deal, as you well know, Jonathan. So, yeah. Have they determined what caused inflation? We're trying to work on testing whether it's the right paradigm or not, and the data we have so far really looks good. We're as I said earlier, you first hear about it, it's crazy. You grow to like it, especially if you're trying to think of alternative theories. You grow to like it. It passed every test we can throw at it so far. What it came from, it would be some field. Recently there's the Higgs particle has been, the God particle, as it was poorly named, has been discovered. Some other inflaton scalar field could do it.
What do you think of the quantum fluctuation?
Well, we know that what you would call empty space has quantum fluctuations. There's a Nobel Prize given for that. But the fluctuations, when you say, I'm going to calculate, based on that theory, I'll calculate what the average energy of empty space should be. And they get a number that is off by 10 to the 120 magnitudes. So they admittedly say, well, but in fact, we don't know how to do the calculation. But they assume that, in fact, it must be zero, it must cancel out, everything must cancel out. But that what we're finding is that it's not zero. It's very tiny, but it's not zero. Yeah. Well, is it the ultimate free lunch? I don't have a good answer for you. Alan Guth would say it's the ultimate free lunch, but in fact, if you say gravitational energy is negative and that it's all zero, and the way to look at it, it's the ultimate free lunch, but total energy is zero. But that's a hard one to get your head around.
How does this compare this telescope to the other ones like the Hawaii?
There are other telescopes doing this kind of work, but if you want to do the cosmic microwave background, you can't just go to a telescope and do it. You have to have incredibly clean beams and stability, to do this kind of work. We're hoping to measure, for instance, in the experiment we're doing now, to a difference in the brightness of 10 to the minus 9 Kelvin, 10 to the minus 8 Kelvin. So most telescopes, you can't do that. So there's no telescopes on Hawaii that could do this kind of work. There's sub-millimeter telescopes, but they were looking for bright, point-like objects, more or less.
So being in
Actually, I'd like to take one last question from another person. Okay. You can come up and ask John. Yeah.
It's a long. Well, I'll give a short story for Ira's benefit. The first grant we had to do this work, which we had to design, build, deploy, and do a year of science. That whole grant was $18 million. The telescope contract and getting that done was about half of it. It's the receiver, these detectors, and getting all that going was another quarter. That's very, very expensive stuff.
Okay, let's thank John for a wonderful lecture.